NASA's newest experimental airplane, the X-59 Quest, is designed with quiet supersonic technology and is intended to help open a new era in faster-than-sound air travel over land. Now under construction by Lockheed Martin Aeronautics Company, the X-59 is designed so that when flying supersonic or faster than the speed of sound, people on the ground will hear nothing more than a sonic thump, if anything at all.
The X-59 is about the length of a professional basketball court and just over half as wide. It's got a really long nose, an engine on top, highly swept wings, and a body or fuselage that's been carefully designed so that the shock waves sound like a gentle thump instead of something much louder.
Once fully tested and pronounced safe to fly, the X-59 will begin making supersonic flights over select communities to measure residents' reactions to any noise they might hear. The scientifically valid data gathered from these community overflights will be presented to regulators who will use the information to come up with new regulations based on noise levels that will enable commercial supersonic flight over land. So, just how will the X-59 lower the sonic boom to a sonic thump? To understand this, you must first know what sound is and how it travels. Every sound we hear is produced by vibrations. These vibrations create sound waves, which can move in all directions through materials like solids, liquids, and gases. A sound wave is a compression or longitudinal wave, where the disturbance moves in the same direction as the wave. Check out this example using a stretched slinky. As the wave moves through the slinky from left to right, the disturbance will also move from left to right, parallel to the wave. The parts of the wave where it compresses are called compressions. A compression is a point where the waves are most compact. The parts of the wave where it stretches, or where it is least compact, are called rarefactions or expansions. Can you see the alternating pattern of compressions and rarefactions? Now let's look at some other characteristics of a sound wave. To determine the wavelength on a longitudinal wave, measure the distance between compression to compression or rarefaction to rarefaction. The frequency is the rate of vibration or the number of compressions or rarefactions that pass a point in a fixed amount of time. In a sound wave, increasing the rate of vibration increases the frequency, also increasing the pitch. The amplitude of the wave is the maximum height of the wave and directly determines the volume or loudness of sound. An increase in amplitude corresponds to an increase in volume. As sound waves travel through solids, liquids, and gases, they move the molecules, which transfers energy and causes the molecules to collide in the direction the sound is moving. As sound waves travel, they lose energy, which is why you can only hear sounds up to a given distance.
So knowing about how sound travels is very important to NASA scientists and engineers as we design supersonic aircraft. Perceived levels of noise of the sound waves reaching the ground can be 105 decibels or higher. In other words, a typical aircraft traveling at supersonic speeds is about as loud as a rock concert. The X-59, however, is designed to be much quieter. We expect the X-59 to reach perceived levels around 75 decibels in supersonic flight, which is a little bit quieter than closing a car door. Generally, commercial aircraft fly at altitudes of 36,000 to 41,000 feet. The X-59 will travel at approximately 55,000 feet above sea level. At this altitude, the X-59 will be flying at a height roughly 44 times higher than the Empire State Building and nearly twice the height of Mount Everest.
So, just how will NASA lower the sonic boom to a sonic thump? Well, you'll have to check out our video on the sonic boom. Thank you for joining us, and we'll catch you next time.